Hey, let's talk about solving systems using tables and graphs. It's going to be fun. So, when you have two or more related unknowns, also known as variables, usually we see x and y, right? You may be able to represent the relationship with a system of equations, which is just a set of two or more equations. That's what a system is. To solve a system, we need to find a set of values that replace the variables in the equations to make each equation true. So we need to find, if we're dealing with x and y, we need to find pairs of x and y values that make both equations true. A linear system consists of linear equations, which have x and y in them. A solution of a system is a set of values for the variables that makes all the equations true. You can solve a system of equations graphically or by using tables. And so these are going to be the non-algebraic ways of solving. So let's take a look at how we would solve this system. First, let's take a look at graphing. If I wanted to graph these two linear equations, let me see. I'm going to have to do a little bit of math here, a little bit of algebra actually, in order to get them into slope-intercept form. Or you could go by intercepts too if you like that. I want to go slope-intercept though. So what I'm going to do is I'm going to add 3x to both sides because I want to get y by itself. So I'm going to add 3x to both sides. And then I get 2y equals 3x plus 8. Then I'm going to divide both sides by 2. And I get y equals 3 over 2x plus 8 divided by 2 is 4. So that means that my y-intercept is 0, 4, and my slope is 3 over 2. So I start at my y-intercept. So on the y-axis, go up 4 units and draw a dot. And then my slope is 3 over 2. That's rise over run. So I'm going to go up 3 and to the right 2. So from here, up 1, 2, 3, to the right 2. And we're at the point 2, 7. And then I draw me a line through those 2 points. Now I want to graph this guy. So I'm going to take x plus 2y equals negative 8. Subtract x from both sides. So I get 2y equals negative x minus 8. Then divide both sides of the equal sign by 2. And I get y equals, so this is negative 1x. So this is negative 1/2 x minus 8 divided by 2 is 4. So my y-intercept for this line is 0, negative 4. And my slope is negative 1/2. So that means I start with the y-intercept. So I'm going to go on the y-axis down 4 units and make a dot. Then my slope is negative 1 over 2. So that means I'm going to go down 1 to the right 2. Down 1 to the right 2. That's the point 2, negative 5. And then draw a line through those points. Now, each point on this line is an x and y value that satisfies this equation. Each point on this line is an x and y value that satisfies this equation. So the point where they cross has an x and y value that should satisfy both equations. So we're looking at it. It looks like it crosses at negative 4, negative 2. So let's just check and see if that's really the solution to this system. Let's see if those x and y values make both of these equations true. So for the first equation, we got negative 3 times x plus 2 times y equals 8. So our x is negative 4, and our y is negative 2. Negative 3 times negative 4 is positive 12. And positive 2 times negative 2 is negative 4. 12 minus 4 is 8. So it works for the first solution. So we're happy there. Now for the second equation, we've got x plus 2 times y equals negative 8. Our x is negative 4. Our y is negative 2. So we get negative 4 minus 4 equals negative 8. Negative 4 minus 4 is negative 8. So it works for that one too. So since this point is an ordered pair that has an x and y value that make both of these equations true, the solution to our system is negative 4, negative 2. Okay, now let's look at another way to find the solution to that same system. So remember, we converted these into slope-intercept form. So I'll show you why we're going to call this y1 equals, because we can just think of this as equation 1 and think of this as equation 2. But even more importantly, we are going to enter these into our calculator. And so y1, you can see right here we got a y1, that's going to be 3 over 2 times x plus 4. And then y2 is negative. Make sure you're using the negative button, not the minus button. Negative 1 over 2 times x minus 4. So I've entered both of our equations into my calculator here. So the next thing I'm going to do is I'm going to look at a table. See this table written in blue right here? I'm going to click second and then table. And it makes a table for me. So it says when x is 0, y1 is 4, and y2 is negative 4. And that makes sense. If you plug a 0 into y1, you're going to get 0 plus 4 is 4. If you plug a 0 into y2, 0 minus 4 is negative 4. And what we want to look for is, we want to look for an x value that makes both of the y values the same. So look at the y values. When x is 0, we got 4 and negative 4. Those are not the same. When x is 1, let's see, the y1 value goes up and the y2 value goes down. So as our x values increase, our y1 and y2 values are actually getting further and further apart. So what we want to do is we want to look in the other direction. Maybe see what happens when x goes down. So when x is negative 1, y1 is 2.5 and y2 is negative 3.5. So they're getting a little closer together. When x is negative 2, y1 is 1 and y2 is negative 3. We're getting closer and closer. And then when x equals negative 4, y1 equals negative 2 and y2 equals negative 2. So that means that our x and y value is negative 4, negative 2. So we see that when x is negative 4, both y1 and y2 equal negative 2. So we can conclude then that negative 4, negative 2 is the solution to the system. Okay, so let's see if you can figure out what the solution to this system is. Okay, so I will show you. First of all, I need to get both of these in slope-intercept form. So if I've got x minus 2y equals 4, I can subtract x from both sides. I get negative 2y equals negative x plus 4. Divide both sides by negative 2 to get y by itself. And I get y equals, let's see, negative divided by negative is positive. So this is 1x. So it's going to be 1/2 x. And then positive 4 divided by negative 2 is negative 2. So we'll call this one y1 equals 1/2 x minus 2. And then for the second equation, 3x plus y equals 5. This one's going to be a little easier to solve. Just subtract 3x from both sides, and we get y equals negative 3x plus 5. So y2 is negative 3x plus 5. Okay, now I'll show you how to do this both ways on the calculator. Click on y equals so I can reset my y1 and y2. y1 is 1/2 x, so that's the same as 0.5x minus 2. And y2 is, make sure you're using the negative sign, not the minus sign, negative 3x plus 5. Now I can look at a graph and a table on my calculator. So if I click on graph, it's going to graph those two lines. And it looks like they intersect right over here somewhere. So I'm going to zoom in on that. I'm going to zoom in some more. I'm going to try zoom box. You hit enter, and then you go down and over, make a box. Now it'll zoom in on that. And let's see, where does it look like they intersect? If we push the trace button, looks like they intersect at about 2, -1. 2, -1. Well, let's see if our table will verify that. So let's do second and then table. And then let's see down here at when x is 2, y1 and y2 are both -1. So I know my solution is 2, -1. Ding! Alright, so we can use a table to solve a problem involving strange-looking sharks. The diagrams show the birth lengths and growth rates of two species of shark. If the growth rates stay the same, at what age, so what age is what we're looking for, would a spiny dogfish shark and a Greenland shark be the same length? Well, doing this problem was worth it already, just because I learned that there's something called a spiny dogfish shark, because that's pretty awesome. Alright, so what we need to do to actually solve this problem is define the variables and write the equation for the length of each shark. So if we let x equal their age in years and let y equal their length in centimeters, you notice they're giving stuff to us in centimeters and years. Then let's say y1 is the length of the Greenland shark. So that's 0.75 centimeters per year times the number of years plus the birth length, which was 37 centimeters. y2 is 1.5 centimeters per year times the number of years plus the birth length of 22 centimeters. Now we can use the table to solve this problem. So y1 equals 0.75x plus 37, and y2 is 1.5x plus 22. And let's go to the table. So second table. So let's see, when it's 0, y1 is 37, y2 is 22. And we can't go back in time. We can't see how long they are when they're -3 years old, because the calculator will figure those out, but that doesn't make sense in real life. Because how long is the shark when it's -1 years old? That doesn't really make sense. So we just need to look into the future and see when their lengths are equal. You see them getting closer and closer and closer. And closer. And they're equal. 20 years down the road, and they'll both be 52 centimeters long. So, the sharks will be the same length when they are 20 years old. So, pause and see if you got this. Alright, so A, if the growth rates continue, how long will each shark be when it is 25 years old? Well, let's take a look at our calculator. When each shark is 25 years old, the Greenland shark, which is Y1, will be 55.75 centimeters long, and the spiny dogfish shark will be 59.5 centimeters, not years long, 59.5 centimeters long. So after 20 years, spiny dogfish guy is actually going to be longer. And then for B, why would the growth rates of these sharks maybe not continue indefinitely? Maybe because if they did, the whole world would be full of giant sharks. I don't know. And then they'd make a movie about tornadoes throwing giant sharks on people. I don't know. Maybe at a certain age, animals stop growing and stay adult-sized. Maybe that might have something to do with it. Ooh, linear regression. The table below shows the populations of the New York City and Los Angeles metropolitan regions from the census reports of 1950 through 2000. Assuming these linear trends continue, when will the population of these regions be equal? What will that population be? I have a table. What should I do? Step 1. Enter the data into lists on your calculator. So, get my calculator. Alright, so enter the data into lists on your calculator. Let's let L1 be the number of years since 1950. So where are the lists on my calculator? Let's see, if I hit the Stat button and I hit Edit, it shows me these lists, L1, L2, and L3. So I'm going to let L1 be the number of years since 1950. So in 1950, there have been 0 years since 1950. Then in 1960, there has been 10 years. Then in 1970, there has been 20 years. In 1980, there has been 30 years. In 1990, there have been 40 years. And in the year 2000, there have been 50 years since 1950. Alright, let's let L2 be the New York City population. Now I am going to not enter 12,911,994. I'm going to round that to 12.9 million, and I'm going to enter it as 12.9 because I don't want to wait for my calculator to graph 12.9 million. It's going to be really hard to see. Okay, so in 1960 it was 14.8 million. In 1970, 16.2 million. In 1980, 16.1 million. 1990, 18.1 million. And in 2000, 21.2 million. And then L3 will be Los Angeles. So in 1950, 4.4 million. In 1960, 6.7 million. In 1970, 7.0 million. In 1980, 11.5 million. In 1990, 14.5 million. and in the year 2000, 16.4 million. Alright, so step 2 is we're going to use the linear regression function of our calculator to find the lines of best fit. Okay, so now, watch carefully. I am going to click on the Stats button again, and I'm going to go over to Calc for calculations, and then 4 is linear regression in the form ax plus b. So I'm going to push 4, and then I got the x list will be my L1, the y list will be my L2, and then I'm going to be awesome and store the regression equation as, and then I'm going to get my y1 variable, and I'll show you where that is. VARS, click over to get to y variables, function, and then select y1. So I'm going to store the linear regression line as y1. Calculate. Okay, so what the calculator has done is it's figured out the line of best fit for those data points, and it's stored it as y1. Alright, so now let's do the same thing for L1 and L3 for Los Angeles. So I'm going to go back to Stat, Calc, Linear Regression Line. Now this time I want to do my x values I want to be L1, but my y values I want to be L3. So I'm going to do second list, and I'm going to select L3, and now it's L1 and L3, and I want to store that regression equation as y2. So variables, y variables, function, y2. Calculate. So now it has stored that equation under y2. So now when I push graph, it's going to show me a line. Should be 2 lines, right? So what that tells me is, well, let's see, this would be at 0 years right here. At 0 years, LA was like 4 point something million, and New York was 12 point something million. So I need to adjust my window here. So what I'm going to do is I'm going to say, alright, well, let's look and see, we go up to, in the year 2000, 22 million almost. So I'm going to adjust my window. I don't need to go into negative years, so I'm going to put from 0 to, and let's look at, I don't know, 100 years. I don't need to go to negative people, so I'm going to do 0, and then let's go up to 30 million, who knows. And now we can push graph, and let's see if it shows both of our lines. Yay! And look, it even shows where they intersect. So I'm going to zoom in a little bit on where they intersect. I'm going to do a box zoom. Bring my little cursor up. Hit enter to start my box. Move it around there. Let's see. That should have our intersection in it. Hit enter, and it will zoom in into that little box. Now I'll show you a cool feature, the intersect feature. So I'm going to do, it's under calculations. These are for graph calculations. So second, calc, intersect is 5. And then it says, what's the first curve? Is it blue? And I say, yes. And they say, what's the second curve? Is it red? And I say, yes. And they say, what's your guess? And I say, right around here is where I think they intersect. So I hit enter, and then they say, here's the intersection, 86.8, which is about 87 years after 1950. And their population would be 25.6 million. So The x value of the point of intersection is about 87, which represents the year 2037. And the data suggests that they'll have the populations of about 25.6 million in 2037. Cool, dude. Okay, so see if you got it. Alright, so I'm going to bring up my calculator. And I'm going to go to, I'm going to hit 4 to clear my lists. And if you look, I'm using the same years here, so I don't want to clear my list 1. I just want to clear my list 2 and my list 3. So I'm going to do list names, list 2. Where's my comma? Comma. List 3. Done. So now when I go to edit my lists, list 1 will still be there, but list 2 and 3 are cleared. So list 2, let's see, I'm going to do these in, I'll do these in millions also, where this would be 1.8 million, but this would be 0.3 million. So L2 is going to be San Diego, so 0. Maybe I'll do 2 decimal places on this one. 3 and 0.57. See, that would round up to 0.70. So 0.70. And then this would be 0.88. This would be 1.11. And this would be 1.22. Then list 3, this would be 1.85. 1.67. 1.51. 1.20. 1.03 and 0.95. Okay, so now let's use our regression equations. So we're going to do stat, calc, linear regression. We can do L1 and L3. Store that as y2. Then we can do the linear regression for L1 and L2. So I just need to change this to L2. List L2. And I'm going to save that as y1. So now I have my 2 regression equations here. I'm going to push graph. And I'm still zoomed into where I used to was. So I am going to wait for it to finish graphing. And then I'm going to do zooms. Maybe I can just figure out my window, in fact. My x minimum is going to be 0. My x maximum is going to be, I don't know, we'll do 100 years, see what happens. My y minimum is 0. My y maximum, let's see, nothing goes up to 2 million, so I'm going to call it 2 million. And now I will look at the graph. There they go. There they intersect. Now I'll do my calculation, number 5, to find the intersection. The first curve is blue, the second curve is red. What's my guess? My guess is right about there. And it tells me the intersection is 40.3, and so that means about 40 years after 1950, so that means in around 1990 they were the same, which that kind of makes sense. And they're about 1.07 million. So sometime during 1990, they were both at about 1.07 million. So, $40.3 years after 1950, it was sometime during 1990, and their populations were about 1,070,000. And your secret phrase is potato chip. Potato chip. Alright, so you can classify a system of linear equations by the number of solutions it has. A consistent system has at least one solution. A consistent system can be either independent or dependent. An independent system has one solution, and a dependent system has infinitely many solutions. Meaning, why they call it dependent is the ordered pair you're going to get depends on what x value you choose. There's a bunch of different ones that you can get. An independent system means independent of wherever you're looking, there's only one solution. An inconsistent system has no solutions. The graph for an inconsistent system is two parallel lines, so there are no solutions. For a dependent system, the two equations represent the same line, so there's infinitely many points where they intersect. A independent system, or an independent system, is the most common, and it's where you have two lines with different slope, one solution. They intersect at one point. So there's one solution, the system is consistent and independent. Coinciding lines means there's two lines that are exactly in the same place. They have infinitely many solutions. It is a consistent system because there is at least one solution. And it's a dependent system because the solution we look at depends on where we're looking. And then we got parallel lines. There's no solution. This is an inconsistent system. So even without graphing, we can look at a system and determine if it's independent, dependent, or inconsistent. All we got to do is write them in slope-intercept form. So for this first one, if I was to get, I need to get y by itself. So I'm going to do a little bit of work up here. 4y minus 2x equals 6. I need to add 2x to both sides. And that gives me 4y equals 2x plus 6. And if I divide both sides by 4, I get y equals 2 over 4 is 1/2 x plus 4 over 6 reduces to 3 over 2. So y equals 1/2 x plus 3 over 2. My slope is 1/2. My y-intercept is actually the point 0, 3 over 2. Okay, for the second equation, we got 8y equals 4x minus 12. Divide both sides by 8. Y equals 4 over 8 reduces to 1/2 minus 12 over 8 reduces to 3 over 2. So we get y equals 1/2 x minus 3 over 2. So they have the same slope, but they have different y-intercepts. That means that they're going to be parallel lines. Same slope, different y-intercept means parallel lines. So the system is inconsistent. There are no solutions. Okay, so pause and see if you can figure these out. And then push play when you're ready to see the answers. Alright, so for A, if I were to add 3x to both sides of this equation, I would get y equals 3x plus 4. For this one, I'm going to have to do a little more work. I'm going to have to subtract x from both sides. which would give me y, negative 1/3 y equals negative x plus 1. Then to get y by itself, I need to multiply by the reciprocal of negative 1/3, which is negative 3. So I need to multiply the left side of the equation by negative 3, and I need to multiply the right side of the equation by negative 3. Negative times negative is positive. 3 over 3 is 1, so I just get y over here. And then I get negative 3 times negative x is positive 3x. Negative 3 times 1 is negative 3. So what I have is two lines that have the same slope but different y-intercepts. Those are parallel lines. So no solutions, which means the system is inconsistent. Alright, so with 2x plus 3y equals 1, I need to get y by itself. Subtract 2x from both sides. And I get 3y equals negative 2x plus 1. Divide both sides of the equation by 3 to get y by itself, and we get y equals negative 2/3 x plus 1/3. Then we take the other equation, 4x plus y equals negative 3. Subtract 4x from both sides, and we get y equals negative 4x minus 3. These are two equations of two lines that have different slopes, which means they're going to intersect, which means I have an independent system. Anytime you have two different slopes, it's an independent system, because your slopes that are not parallel are going to intersect in one point. One point is a consistent, independent system. Okay, so 6x minus 3y equals 9. If I subtract 6x from both sides of the equal sign, I get negative 3y equals negative 6x plus 9. Then if I divide both sides by negative 3, I get y equals negative 6 divided by negative 3 is positive 2x. And then 9 divided by negative 3 is minus 3. So that means that this equation has the exact same slope and the exact same y-intercept. So these are two coincident lines. So that means there are infinitely many solutions, which means it is a dependent system. Merry Christmas. That was a long video. I congratulate you for making it all the way through, and I will see you on the internet.